In this lesson, we're going to be looking at a particular type of problem that you solve with linear systems, and these are known as DVT problems, or distance, speed, time problems. So some things I want you to be keeping in mind when you're trying these on your own or as I go through these examples. One of them is make sure that you're actually paying attention to what the question is looking for. What does the question want? What is it asking you to find? That may help you decide what your variables should be and how you should go about solving it. All DVT problems make use of the relationship distance is equal to speed times time. Now that can be rewritten a couple of different ways. If I start with d equals vt, I can rearrange this for v if I divide both sides by t. So divide by t and divide by t, and you end up with d over t is equal to v. Or if you wrote that the other way around, it would be v is equal to d over t. The way to remember this one is if you think about a speed, if you're driving along in a car, your speed is going to be, for example, if you're driving along the highway, you might be traveling at 100 kilometers per means division, hour, 100 kilometers per hour. So 100 kilometers is obviously a distance, and per 1 hour is obviously a time. So you can use this to help you remember how to write this. And then the other way you can rearrange, if I go back to my original formula, d equals vt, you could also rearrange this for time. And the way you do that is divide both sides by v, divide both sides by v. And you end up with the final result for this one is time is equal to distance over speed. Now there's no correlating analogy for that one. Nothing as convenient as 100 kilometers per hour. So normally for this one, time is equal to distance divided by speed. You start with your original expression and you go from there. For those of you who have seen this triangle before, the problem with the triangle is you have to remember how the triangle is laid out. Otherwise, if you get the letters in the wrong places, the triangle won't work for you. But the way that the triangle does work, if it's going to work, is you cover up. So it works better if you have a hand that you can actually do this. So you cover up what you want to find. So in this case, I've covered up v. And then you can see what's left over is d over t. And that works just the same way. V is equal to, sorry, it's right here. V is equal to d over t. I could do the same thing if I covered up. Okay, so now I'm going to cover up, if I cover up d, that means I'm finding d, and that's equal to vt, or v times t, which is our original formula, and so on from there. So you've got a couple of options on how you can approach this. I'm going to show you a table, so I'm going to show you a method that you can use. It's very systematic to help you come up with equations and to maybe give you an idea about unknowns. And the other thing you really need to make sure of here, this idea of making sure your units are consistent. And by that, I mean if you have something, for example, in kilometers, and then another measurement is in miles, well, kilometers and miles are not consistent units. You would need to convert between them. Another example where you might have that would be as if you have something in hours and something else in minutes. Hours and minutes are not consistent with each other. So when you get down to it, make sure all your units are consistent, and it's a good idea to make sure your units are consistent before you start doing any serious work. So with that to think about, let's move on and take a look at our first example. So in our first example, we have Alex drove 500 kilometers from Ottawa to Toronto in 5.5 hours. He drove part of the way at 100 kilometers per hour, and he drove the rest of the way at 80 kilometers per hour. So how far did he drive at each speed? And this is a pretty typical question, and for most of these questions you can set up this fairly typical table. You can see this table is broken up into 2 trips and then a total. If you look at what we've been given here, we actually have been given information about the total. First of all, the total is from Ottawa to Toronto. Okay, so that's the first part. Let's see, what do we know? The distance from Ottawa to Toronto is 500 kilometers. So the distance from Ottawa to Toronto, that's our total distance traveled. That's 500 kilometers. He drove, let's see, he did that in a total time of 5.5 hours. Rather than writing that as 5.5, I'm going to write that as 5.5 hours. All is good so far. He drove part of the way at 100 kilometers per hour. So I'm going to call that trip number 1, and I'm going to put 100 kilometers per hour. Now this is a good time for you to take a moment and check those units. We want to make sure units are consistent. So far I've got distances in kilometers, I've got time in hours, and my speed is in kilometers per hour, so that's good. Doesn't look like I'm going to have to change anything here. And the second trip was at 80 kilometers per hour. So this raises some interesting questions. I've got these two speeds. I have no idea how long this trip took, and I have no idea how far each of the pieces were. If you look at this looks like there's way too much stuff that's unknown here. But we can get past this if we remember. Well, before we do that, let's just go ahead and say that this is distance 1, and this is distance 2, and this is time 1, and this is time 2. That's a lot of variables. 4 variables. I can't solve for that. But if we remember the relationship between distance, speed, and time, and you try to set up, I recommend you set up this table so it flows quite nicely. The equation is d equals vt. So if you remember that equation, always set up your table with distance equals speed times time. And if we do it that way, then suddenly we are able to get rid of these d1 and d2 variables because this distance is equal to this speed times this time. Well, that means that distance 1 is actually, I'm going to get rid of all these equal signs, they're going to start to get confusing. Distance 1 is actually 100 times t1. 100 times t1. And distance 2 is actually 80 times t2. So now what I've really done is I've gotten rid of distance 1 and I've gotten rid of distance 2. Instead, I have 100 t1 and 80 t2. t1 and t2. So my variables here are just t1 and t2. Now that I have two variables, can I come up with the two equations, the two linear equations that I need to solve this? Before I move on, one last thing I want to comment on. My distances added up to 500. My times added up to 5.5 hours. And then finally, my speeds. And the one thing I want to comment on is if you're going to do additions this way, it doesn't actually make sense to add speeds together. So we normally X out this box. 100 kilometers per hour plus 80 kilometers per hour, that doesn't make a lot of sense to talk about a total here. There could be a question where maybe you're interested in an average speed, but even then, that's probably not going to work out for you. So really, I want you to stay away from that idea. Normally, we're going to make use of speed in terms of the other quantities, distance and time. So now that I've got that, let's go ahead and construct our equations. So the way I construct my equations is I'm actually going to look at this vertically and look at this one vertically. So I end up with 100 t1 plus 80 t2 is equal to 500. That's equation number 1. t1 plus t2 is equal to 5.5. That's equation number 2. And now I'm just solving these equations. I've got all the information that I need from that table. So actually I'm just going to run that table right off the top of the screen because now I'm just working with these equations. We'll have to go back to the top and consult the question again once I'm done solving here to make sure I've actually solved things that I need to. Now the first thing you might want to do is to make this equation a little bit easier to work with. You might actually do that for both of them if you don't like this decimal. But what I particularly don't like are these really large numbers. I notice that each of these numbers ends with a 0. So that immediately tells me that I can divide all of these numbers by 10. So if I divided everything by 10, that's like taking away a 0. So divide by 10, divide by 10, divide by 10. I could have done better than this in one step, but this becomes 10t1 plus 8t2 equals 50. And maybe you noticed this before, I also could have divided by 2. So I could have divided by a total of 20. But I'm just going to go ahead and do that now. Divide by 2, divide by 2, divide by 2. And that becomes 5t1 plus 4t2 equals 25. I could now do substitution. So I could isolate t1 or t2 and sub it in here. Or it's actually pretty easy for me to get one of these coefficients to match up. And in particular, I could pretty easily get the t2 coefficients to match up. The way I do that is I multiply equation number 2. If I multiply equation number 2 by 4, that becomes 4t1 plus 4t2, and 4 times 5.5 is equal to 22. 2 times 5.5 is 11, and then double that again is 22. So I'm going to call, let's see, this one I changed, I'm going to call this equation 3, and this one I'm going to call equation 4. And now I'm going to actually rewrite equation number 4 down here. Let's just erase that little part there. And I end up with 4t1 plus 4t2 is equal to 22. Now I really want to caution you, you're going to be, as you go through this process, you're going to be writing and rewriting and modifying equations a lot. If you make a single mistake, changing a sign, getting a coefficient wrong, if you're someone who is prone to that sort of thing, you have to be so careful as you're doing this. Otherwise, you're just throwing away the good work that you've done up until that point. These 4s match up. They have the same sign. So if you remember our lesson on solving by elimination, I have to do subtraction. So I'm now going to do equation 3 minus equation 4. 5t1 minus 4t1 just gives me 1t1. 4t2 minus 4t2 gives me 0. That's the elimination part. 25 minus 22 gives me 3. So t1 is equal to 3. I've got my first answer. Now might be a good time for us to go back and consult the original question, find out what we're actually trying to find, just to refresh our memory. How far did he drive at each speed? So the distance that he drove at each speed is contained here, 100 t1 and 80 t2. So I actually need to solve for t1 and to solve for t2. So let's just keep in mind, how far did he drive at each speed? That's what I'm interested in. Okay, so now let's solve for the other time variable. t1 is equal to 3. I can sub t1 equals 3 into equation 1, equation 2, equation 3, and equation 4. The easiest one of those to solve is actually equation 2. So I'm going to sub t1 equals 3 into equation number 2. And that becomes, instead of t1, I have a t1 here. Instead of that t1, I'm going to sub in the value 3 plus t2 is equal to 5.5. How do I get t2 all by itself on that left side? I have to subtract 3 from both sides. So 5.5 minus 3, and that becomes t2 is equal to 2.5. Okay, so now I've got both my times, and I'm just going to kind of block off the work that I've done so far. And over in this space, I'm now going to go on to my next and last steps, which is to find out, well, in that case, what is d1? If I know t1 is equal to 3, what is the first distance traveled? d1 is here. It's equal to 100 t1. 100 t1. And that is equal to, d1 is equal to 100, but instead of t1, I'm going to sub in my 3. And d1, some very simple arithmetic involved here, d1 is equal to 300. d2 was equal to 80 t2. I just remembered that from our question, so I don't need to go look at it again. If you're not sure, you can always double check. 80 multiplied by t2, which is 2.5, and I end up with d2 is equal to 200. 180 times 2 is 160, 80 times 0.5 is 40, and so that's equal to a total of 200. I could have come up with that another way. If we went back here and took a look, we knew the total was 500. So once we knew 300 for the first one, we knew the other one had to be 200. And so how far did he drive at each speed? Therefore, looks like he drove 300 at 100 kilometers per hour and 200 kilometers at 80. Therefore, he drove, and you finish with a concluding statement, 300 kilometers at 100 kilometers per hour and 200 kilometers at 80 kilometers per hour. You can see these word problems, they take quite a bit more time than our simple solving systems of equations, but we're still solving systems of equations. It just takes a bit more to get there, and sometimes there's a bit more work to do on the tail end to finish off the equation or the question properly. Let's take a look at another example. Okay, for this one, Emily traveled 95 kilometers from Oakville to Oshawa by car and GO train. So the total from Oakville to Oshawa is 95 kilometers. So this is Oak to Osh, and that was a total of 95 kilometers. Part of that trip was by car, and part of that trip was by GO, the GO train. The car averaged 60 kilometers per hour. So we take our first check here of units, kilometers and kilometers, that's good. The train averaged 90 kilometers per hour. And once again, units are consistent, so we don't have to do any conversions off to the side. The whole trip took 1.5 hours. How long was she in the car? So this question is primarily concerned with the time in the car. That's the piece of information that we want the most. If we go from here and actually use the exact same reasoning we did before, we can call this T1, we can call this T2. We're not going to add up the speeds, and this distance one is actually equal to 60 times T1. This distance 2 is equal to 90 times T2. And from that, we can form, here's our first equation using those values. Here's our second equation using them. You can see these are the exact same type of equations from our previous example. The difference is the previous example wanted to know the distances for each of the types of transportation. This one wants to know T1. So if you really want to speed up your ability to solve this, you think about that and then you arrange this so you solve for T1. So let's take a look at our equations and work through them. So 60 T1 plus 90 T2 is equal to 95. It's equation 1. And T1 plus T2 is equal to 1.5. That's equation 2. Just as we did before, I can simplify this. Now I can't divide by 10 because 95 ends in a 5, but these end in zeros and this one ends in a 5. That means they actually have a common denominator, or sorry, a common factor of 5. So this time I'm actually going to divide everything by 5. And from that I end up with 60 divided by 5 gives me 12 T1 plus 90 divided by 5 gives me 18 T2, and 95 divided by 5 gives me 19. Now I've got T1 plus T2 equals 1.5. We could, once again, elimination would work very well here, especially when we think about what we want to eliminate. So what is it that we'd like to eliminate? We'd like to eliminate T1. Sorry, we want to solve for T1. We'd like to eliminate T2. So we could do that either way, but since I did elimination in the previous question, I'm just going to choose to do substitution here. And I know I want to get rid of this, which means I want to keep T1. I want to get rid of T2. I want my final answer to be in terms of T1. So the way I do this is I'm going to isolate T2 equals, and instead of 1.5, I have to bring this T1 to the other side, so that becomes 1.5 minus T1. And now I'm going to sub T2 into, and this I guess we would call equation 3. My preference actually would have been to do this by elimination. If I was just doing this for myself, I probably would have done elimination, but to illustrate this better, I think it's better to do substitution in this case. 12T1 plus 18 times, oh, I didn't want that to go that far back. Just want to change the color here because now I'm going to sub. Wherever I saw a T2, I'm going to replace that with this value. 1.5 is not even a value, it's an expression. Equals 19. So I've got to do some expansion here now. I'm going to take this 18 and multiply it into this bracket using the distributive property. And so I end up with 12T1 plus 18 times 1.5 is equal to 27. Positive 18 times negative T1 is minus 18T1, and that's equal to 19. I already have all of my T1s on this left side, so I'm just going to go ahead and keep them there. And I'm not going to skip any steps here. So I'm going to say that's 27 minus 12T1 minus 18T1 is negative 6T1 equals 19. Now you'd have the option, if you prefer, you could take that over, make it positive. I'm not going to bother. I'm just going to go ahead and subtract 27 from both sides. I end up with negative 6T1 is equal to 19 minus 27. That's equal to negative 8. And then I divide both sides by negative 6. And I end up with T1 isolated. That was the whole point. That was why I divided by negative 6. Negative 8 over negative 6. Negative over a negative becomes a positive. And 8 over 6 is the same as 4 over 3. And just to remind ourselves that we're actually solving for the correct thing here, the whole trip took 1.5 hours. How long was she in the car? Looks like she was in the car for about 1.33 of those hours. Now, if you want to be on the safe side, then you need to complete this question. If you don't trust the math that you've done here, you would need to go through and complete this question and also substitute in the distances and make sure that it worked out properly. So to do that, you would then solve for T2. So now let's say I'm just going to change the color here and I'm going to sub T1 equals 4/3. So now I'm going up to here. And I end up with T2 equals 1.5 is the same as 3 over 2 minus 4/3, which is equal to 3 over 2 and 4 over 3. Common denominator for each of these is going to be 6. So this becomes 9 over 6. And this one becomes 8 over 6. And that's equal to 1 over 6. So we were in the car for 4/3 of an hour. We were on the GO train for 1/6 of an hour. And let's make sure those distances actually work out. So then we would have to substitute D1 is 60 times T1. D1 is equal to 60 times T1. d2 is equal to 90 times t2. All of the stuff I'm doing here in red now, this is just a verification. This is just because I don't want to take chances. 60 times t1 is 60 times 4/3. And 90 times t2 is 90 times 1/6. And that's equal to, well, 3 goes into 3 once, and 3 goes into 60 20 times. 20 times 4 is equal to 80. Let's see, 6 goes into 6 once, and 6 goes into 90 15 times. And 15 times 1 is equal to 15. Take a look at those two distances, 80 plus 15. And our original question told us it was a total of 95. 80 plus 15 adds up to 95. So we had the right answer, but we went a little bit further just to double check our answer. But in the end, therefore, the time in the car was, now you can do this, there's a couple of ways you can do it. You could say it's equal to 4/3 hours. That's not very good. People don't want to be told that 4/3 hours, that's not really meaningful time to someone. Or approximately 1.33 hours. Well, that's okay. Or 1 1/3 hours. I've mentioned before, we don't use mixed numbers very much in this course, but here's one where it might be okay. Or, and I think this is the best answer, which is 1 hour and 1/3 of an hour is how many minutes? 1/3 of an hour is 1/3 of 60 minutes. That's equal to 20 minutes. And that, I think, is the best possible choice for our answer here. 1 hour and 20 minutes. It's the most meaningful answer to someone who's asking this question. All right, I believe this is our last question. I think this is going to be a long lesson. A boat took 2 hours to travel 24 kilometers down a river with the current. So it was traveling with the current. So if you're traveling with the current, that means that the flow of the water is actually moving you along a little faster. And 3 hours to make the return trip against the current, because now not only do you have to paddle up the river, but every time you paddle up, the water pushes you back a little bit. If you need another way to think about this, imagine an escalator in a shopping mall. If you go on the escalator going up and you walk up at the same time, the escalator gives you a bit of a boost and you travel up. Now, most of you have probably never done this because your moms wouldn't let you and were worried that you were going to get caught in the escalator and get killed. But if you ever tried walking down an escalator that's going up, you'll find you don't make progress very quickly, and that's like going against the current. I don't recommend you walk down the escalator. You're probably going to trip and end up getting killed. So don't do that. But same idea here. So when we talk about finding the speed of the boat in still water, that is asking us what would be the speed of the boat if the person was paddling with no current, or imagine the person was paddling in a swimming pool, and we also want to know the speed of the current. So that gives us an idea of what our variables might be. So let's take a look. Our first trip was downriver, and that means with the current. Our second trip was upriver, and that means against the current. And we went 24 kilometers down the river and 24 kilometers up the river, and that would make for a total of 48 kilometers. And as you can see, this vertical column, which we've used to make an equation in the past, it's meaningless. Of course, 24 plus 24 is equal to 48. That doesn't tell us anything. Okay, we were told we traveled 2 hours down the river, 3 hours up the river, and once again, 2 hours down the river and 3 hours up the river, that adds up to 5 hours. It doesn't tell us anything. This is where we get into some interesting things, which is when I was going down the river, that means I'm going with the current, I was paddling at, let's say I was paddling at some speed X, And what was the current doing? Was it adding or subtracting to my speed? If I was going with the current would be adding some amount to my speed. So I'm going to call my base speed x, and I'm going to call the speed of the current y. So when I go down the river, I'm going faster than I would normally be able to go just with my muscles. When I'm going up the river, I end up going slower than my muscles can power me because the river is pushing me back. When we did our previous questions, we relied on this column and this column to make our equations, but as you can see, there's nothing meaningful there. But we also used these horizontal rows to come up with kind of supplementary equations that helped us work things out. In this case, however, we end up using these rows. These are going to become our primary equations because the relationship distance equals speed times time hasn't changed. So let's take a look at that. Distance equals speed times time. I didn't mention it before, but let's check our units as well. Kilometers and hours. So be aware that any answer I get for x and y is going to be in kilometers per hour. So let's scroll down and let's fill out our equations. The first equation is going to be 24 equals speed times time, x plus y multiplied by 2. And that's equation, well, I'm going to expand this before I label it equation 1. My other equation starts as 24 equals x minus y multiplied by 3. And so let's expand this out a little bit. 24 is equal to x times, so this is it's still the distributive property, just think of it from the other direction. Same, the distributive property here from the other direction. Still works the same way. And so 2 times x is simply 2x. 2 times y is 2y. That is equation number 1. 24 equals 3 times x is 3x. 3 times negative y is minus 3y. That's equation 2. I didn't even need to label them yet because I'm going to make a modification. 24 and 2 are all even numbers. So I'm going to divide everything by 2 to simplify this. And from that, I get 12 equals x plus y. Call that equation 3. And similarly, over here, 3 and 3, and it turns out 24 is divisible by 3, so I'm going to divide everything by 3. This won't always work out so nicely, but we should be grateful that it did here. And we get 8 equals x minus y. That's equation number 4. These two equations are perfectly set up. They're in the same form. One of them they have the same size coefficients, but one of them is negative and one of them is positive. This is meant for elimination. So I'm going to rewrite equation 4 down here. 8 equals x minus y. Couldn't be any simpler. I'm going to take these two and I'm going to add equation 3 plus equation 4. 12 plus 8 is equal to 20. X plus x is equal to 2x. Y minus y is equal to 0. Divide both sides by 2. And I end up with x equals 10. You can see I just went ahead. I was going to get the answer 10 equals x. I just went ahead and changed it to x equals 10. You can do that. Now that I know what x equals, now I know that x is equal to 10. This one has a negative y. I want my answer to be a positive y, so I'm going to sub x equals 10 into equation number 3. And I end up with 12 equals, but instead of x, I'm going to replace that with a substitution of 10. And that was plus y. To get this 10 over to the left side, it becomes negative 10. 12 minus 10 is equal to 2 is equal to y, or y is equal to 2. Remember that x and y, you have to remind yourself of what they represent. X represents your speed with no current, and y represents the speed of the current. And so, therefore, is it a person? Is there a name that goes along with this? Nope, it's a boat. So therefore, the boat's speed with no current is 10 kilometers per hour, and the current is 2 kilometers per hour. A little bit of something I call a sanity check here. If you got answers here that were the other way around, does it make any sense at all if the speed of the current would be higher than the speed of the boat? Think about that. Think if you were trying to paddle upstream, but the current was faster than your muscles could make the boat go, or the engine. Well, then you would just get pushed back downstream. You could never go upstream again. So that's a good way to also double check your answer, just to make sure you're not double checking the numbers, but you're at least making sure the numbers make sense. And I think that's the end of our lesson. Yes, it is. Okay, good luck with DVT problems.